All right, how about some problems from 9-2, starting with numero uno, which means number one. So our derivative here, they have it written as y prime. That's fine. I think I generally prefer to do the dy dx thing. And it's the slope at any point of the solution curves here is given by x times y over 4. And they want us to do a little 2 by 2, negative 2 to positive 2 kind of grid like this. Going to be 25 of them. Oh my goodness. All right. So where either one of these is 0, then the slope is going to be 0. So that's all the places where y is 0, and all the places where x is 0. Let's get those out of the way. And then here at 1, 1, the slope is going to be 1/4. And then at 2, 1, it's going to be 1/2. And then that's the same here. And then that'll be a slope of 1 there when they're both 2, right? And then this is all the same, except now one of them's negative and one of them's positive. So it's like a mirror image of this. If you do have to do a slope field by hand, you want to look for patterns, little shortcuts, because it'll make it easier. This, same, but they're both negative, so something like that. That's my slope of 1/4. Those are 1/2, and that's 1. And then here, same idea with the negative slopes, because I'm in the second quadrant. So it looks something like that. So what do solution curves look like through here? If you pick a point, you just kind of go with the flow, and see what happens. So here, like this would be, they look like, I think they look like hyperbolas, probably. If you started on a horizontal, then it would just go like that. It's like an asymptote. All right, that looks good. Number 3, moving on. Number 3, we want to look at the slope field given here. And it looks like I have somebody's book who thought that it was appropriate to draw in their calculus book. Whoever had this book last. That is not generally a good idea to draw in your calculus book. You could trace, though, so maybe we'll do that. So we want to make 3 solution curves. This is the slope field, and we want to start at the point 0, -1 first. So 0, -1 is right there. I don't know if you can see. How well can you see that? Not very well. I don't think I have any thinner paper than this. That would have been a good thing to try to procure before this. So let's see. The at -1, it's right around here. Looks like it's kind of like this sort of steepness, and it's looking kind of like logarithmic. All right, it's gonna like hug up to, there's the axes, something like that. And there is an asymptote. It's not actually a logarithmic curve, because logarithmic curves don't have horizontal asymptotes. So something like that. How about if we started at the point 0, +1? At 0, +1, that puts us right on that line. And unless we have the horizontal variable as time, there's no reason why we shouldn't also go backwards for the sketch. We shouldn't only go forward unless it's time and it specifically says that we should only do that. And then what about 0, 2? So at 0, 2, looks like we're here, and now we're coming down to that asymptote. So that looks good. So those are 3 curves in the family of the solutions for this. All right. What do we have next? We have number 9. Oh, matchy, fun. Let's see. So we want to match these. I guess I'm going to have to slide this up and down a little bit. So match these with these. Okay, so we'll just go through in order and see what we can figure out. So if the derivative is 1 over x, then what do the solution curves look like? Well, the antiderivative of 1 over, you can actually solve that one, but let's not do that. Never mind. Just imagining here, the bigger notice that this does not depend on y values. So as the y values, as we move up and down, that's not going to change the what the slopes are. The slopes only depend on the x values. So let's just look and think about like what things could possibly be candidates for that. This could be a candidate for that, because if you pick an x value and look up and down, they're all the same. This is something that depends only on x values, not on y values. This looks like something that depends only on y values, and as the x's change, the slope doesn't change. So this is something that only has x's. This is something that only has y's. This is something that looks like it only has x's. Right? You go over, pick some x value, and then you go up and down, and it doesn't matter. And this looks like it only depends on y values, right? See how they're kind of in strips along the different y values, and they don't change. You change the x value, doesn't matter. It's the same. And then this one and this one are kind of swirling around, and they do not depend so that means they don't depend just on x and y. They're going to have some dependency on both coordinates. Okay, so blah, blah, blah. So I think our 2 choices are 4 and 5 for ones that only depend on x. And we might note that when x is 0, it would be undefined. That looks like that could be going on here. And then as the x values get bigger, the slopes get smaller. So yeah, this looks good. This is the one. So A goes with 4 there. How about B, 1 over y? Well, that's kind of the same thing as this, but sideways, right? So when the y value is 0, then the slope is undefined. So when y is equal to 0, the slope is undefined. Where's that? Where's that one? Oh, they actually drew in the slopes undefined. It's right here. It's this one. So those slopes are undefined there, and then as the y values get bigger, those get smaller. So it's not really like a rotated version of that. That's interesting to note that it does look quite different, whether it's 1 over x and 1 over y. So that's B goes with number 6 right there. And then C, what if y prime is equal to e to the negative x squared? Well, that only depends on x, so that's got to be something that has, once you pick an x coordinate, you go up and down, it doesn't change. So I think this is the only other option for us, but let's just convince ourselves that it does look like this. So when you plug in x equals 0, you would get a slope of 1. And then when you plug in something like x equals 1, that would be 1 over e. And then as you plug in bigger x values, you'd get smaller fractions, things going to 0. And then it's an even function, so the slopes on this side and the slopes on that side are the same. So that looks good. Number 5 for C. Letter D, y squared minus 1, so that only depends on y, and that must be this here. So we note here that when y is equal to 1 or negative 1, we get slopes of 0, which makes sense. So you can check some more values, see what's going on there, but that's the correct answer for D. And then E and F are these two swirly ones. So let's see if we can figure out which one is which. E, we got x plus y over x minus y. So I think I would be tempted to look for some values where the slope is undefined. So x minus y, when x and y are equal to each other, that's along this line here, we would have undefined slopes, and that looks correct here. Those undefined doesn't mean you don't draw it in. You would only not draw it in if it had a 0 over 0, because then it would be indeterminate. But undefined, like number over 0, that means it's vertical. So look at all those little vertical lines there. Okay, what if the top was equal to 0? When is x plus y equal to 0? Well, that's when y equals negative x. So then along this diagonal we should have 0 slopes, and we do. So I would be convinced by that that's the correct one. So F must be 3. But let's take a look. So sine x and sine of y at 0, 0, those are both equal to 0. So that would give us a 0 slope. Hard to see that because it's right on the axis. And then anywhere where x is equal to 0, the sine of 0, so we should have 0 slopes all up that axis, and likewise for y, although we can't really see those. And other places where there should be some kind of like periodic nature to this, so we could probably figure out what the scaling is. When y is equal to, this must be at pi right here, the scaling, because or maybe it's actually at 3, and it's like we're just close to pi. Maybe they actually did scale it that way, because you can see those are a little wobbly there. So this is almost at pi, and you can see we're almost getting everything to be 0 again, and then almost at pi. So all these are almost 0 again too. So that's getting that swirly pattern with the sine x and the sine y. All right, cool. Number 11a. Only 11a, not the other parts of 11. So I guess we didn't need to write anything down there. 11a, we want to do Euler's method with a step size of 0.2. And we're going to do from 0, we're starting at y of 0 is equal to 1, and our target is to get to x equals 1. So I'm going to make my little Euler's method chart. Here's my x value. I'm starting at 0, and my step size is 0.2. And that's what I'm going for, and then that would be my target. That's my y value. Okay, my slope is x plus y, and my delta y, my step, is equal to dy dx times the step size, delta x, which is 0.2. Right? So delta y is approximately equal to that. Okay, so my slope, x plus y, here is 1, and then the delta y, I take this 1 and multiply by 0.2. And then that's the delta y, so I just add that to the y value. So now I have 1.2. Okay, add them together, 1.4, and multiply by 0.2. So that gives me, what, 0.28, I think. And then I add that to this. And then I add those together. And then I reach for my calculator. And 1.88 times 0.2, 0.376. And then I'm going to add that back to my y value. That gives me 1.856. And then I'm going to find my slope, which I get by adding those together. 2.456. And then I'm going to multiply that by 0.2. And I'm going to keep 3 College Board decimal places. Actually, I'll keep 4 until I get to the end. It's probably wiser. And then I'm going to add that to this. And then I'm going to add these together because that's how I get the slope. Ooh, that's almost pi. And then I'm going to multiply that by 0.2. And then I'm going to add that to this. .977. Let me check and see how that looks with the, yeah, that looks good. The book has 2.98, 2.977. I'm not going to spend too much time here showing you this, but I wrote a program for my calculator called Euler's method, where you put in the dy dx, which here was x plus y, and your initial x value, which is 0, initial y value, and then your delta x, and we want to approximate it at x equals 1. And it does that. If you're wondering, like, how come that got something slightly, it didn't really get something different. It's the same rounded to there. It is slightly different than what I had, but that's because I was rounding here, and this is keeping the whole thing. So if you're into coding at all, or like thinking of things in this kind of algorithmic way, I mean, this is just like screaming, like, please program a computer to do this. Don't make me do it. This was a very easy program to write. If you ever see me in person, there's ways of getting it from one calculator to another, but they never ask this kind of question. For College Board stuff, I might have told you this in the notes, that they're never going to ask you more than 2 steps of Euler's method. That's their go-to. They want to see that you can do it, but they don't want you to do so many steps that it becomes more and more likely that you're just going to make some kind of little ticky-tacky error. So, speaking of Euler's method, here's 2 more. So let's see, 13 is dy dx is equal to the cube root of y. We're starting at 0, 1, and we're going to 4 with a step size of 1/2. So I don't really like doing this any more than you do. In fact, I might like doing it even less than you. I wrote a program to get out of doing it. dy dx is equal to cube root y, and then, of course, delta y, the change in y, is going to be equal to whatever I get there for my slope times the delta x, which is 1/2. All right, here we go. So Oh, I just want to use my program, but we want to see all the steps. So if you got halfway through and you made an error, it's nice to see what's happening. Okay, so let's see what we can do. The dy dx is the cube root of y, which here is 1. Cube root of 1 is 1. And then multiply the slope by 0.5. Add it back onto here. Okay, now I need to find the cube root of, is that math 4? The cube root of 1.5. And I'm going to write down that's 1.145. I'm going to write that down. I'm actually keeping the number in my calculator. I'm just going to keep that and do times 0.5. And then I'm going to keep this number and bring that over. So I'm keeping more than what I'm writing here in case I get something that's slightly different than yours. So then I'm going to add that to plus 1.5. And then I'm going to do this like cube root of answer is 1.275. Forgot to write this down. This was 2.072. 1.275, and then I multiply that by 0.5. And then I add that to 2.072. So I guess I am rounding this, amn't I? So we'll see how close we get to the book or to each other by the time we get to the end. All right, I think I'm still okay here. I don't think I messed it up. 2.709. And then I want the cube root of that. And then I need to multiply that by 0.5. And then I need to add that back to this. If you really like this, you're like, oh, I love this Euler's method. Maybe you should become like an accountant or something. Then I want the cube root of that. I have nothing against accountants, by the way. One of my, I'm going to say favorite students. I don't have favorite students. I love all you guys. But a student that I remember very well who I've been in touch with on and off over the years. She's gone away, married now, like fully fledged adult type person, and she's an accountant, and I bet you she's probably, let's see, she's still in her 20s? She's probably still in her 20s. Bet you she makes more money than I do. So look at me, I'm losing my place. Okay, so I need to multiply this by 0.5, but I have a lot of fun. Maybe she does too, I don't know. So then I add that back to 3.406. Meaning of life through the lens of Euler's method. Then I need the cube root of that. Oh, syntax error. What? Why is that a syntax error? All right, let's see if it's going to let me do this. Math. There we go. 1.608. Thought I lost it there. Half of that. Add that to that. I feel like in these problems it's like a miracle if you get the right answer at the end, that you didn't mess anything up. That was a data entry. Let's write a computer program already. 4.962. I wonder what the cube root of that is. Math. Oh, I know what my syntax error was. I didn't put anything inside the square root, so I just hit enter. And then half of that. Add that back on over here. There's light at the end of the tunnel. And I wonder what the cube root of that is. Oh dear, that's going to be syntax error. Yikes. What did I do there? Math for answer. There we go. Okay, got it. 1.798, half of that. And then finally, mercifully, we add that for the last time, 5.815 back to there, and we get 6.714. Boom. All right. What did they get? Let's see what they got, and then let's do my little program. They got what? 6.9. Oh wow. They got something really different. They have 2.11 here. Well, this is interesting. Maybe because they only kept fewer decimal places. It's 6. And then yeah. So I think like as early as this, they just kept this as 0.6. Now then, how would they have 2.11? Huh. I don't know. Maybe I made a mistake there. But I ain't going back and doing that again. Let's see what the program says. So program, Euler's method. What's my dy dx? It is the cube root of y. And what's my x initial? Where are we starting at? 0, 1. 0, 1. Change in x is going up by half. Approximate x equals 4. Oh. Hey, that's what I got. Or nearly. I don't know what the book did, but I like our answer better. I'm just going to call this our answer. So, there you go. Victory is ours. And then the last one, number 15. Is this one only 4 steps? This is only 4 steps, so I'm not going to cry. I'm just going to math up and do it. So what do we have? We're starting at 0, 1. We're going up by half-C's till we get to 2. That's my target there. Dy dx is the cosine of y, and then once I get that, my delta y is equal to dy dx times delta x, which is 0.5, right? That's my increments. Okay, so I better make sure that I'm in radian mode. I bet I'm not, because I'm doing calculus. So that'll mess you up. And let's go, Wildcats. The cosine of 1 is, I don't know, garbage. Cosine of 1 radian is 0.540. And then if I multiply that by a half, 0.270, add that back onto this, 1.270, take the cosine of that, 0.296, take half of that, 0.148, And then add that back on here. So the only rounding that I'm doing, the way that I'm doing this here is when I get back to here and I add that back on, I only kept track of 3 decimal places. So whatever, that's how I'm doing it. 1.418. The cosine of that, I mean, seriously, who cares what the cosine of that is? Hey, there it is, 152. And then half of that is 0.076. You know, I feel like I'm giving Euler's method a bad rap here and sending out some negative vibes about it. And I actually think Euler's method is like super cool. I just think that it's better done by a machine than a human. I'm sure you agree right about now. Guess that's as many as I'm writing down. 3 College Board decimal places. All right, 1.532. It's really cool because we're doing like little, I know I talked about this in the notes, but we're like doing like a tangent line and we're saying like, okay, let's make a tangent line approximation and then let's figure out what the slope is again. Take another little step along that, figure out the slope again, and it guides you through. It's a really cool method, especially when you can't solve your differential equation. All right, so that was number 15. They have 1.53. We agree. Book and I agree, so there you go. I'm not going to do the little program then. All right. I guess about 1 minute and 50 seconds into the free pizza.